In the two previous videos, we saw how we could achieve Markovnikov addition of a hydrogen and an oxygen to an alkene. In this video, we're going to look at a method for obtaining anti-Markovnikov addition, and that procedure is called hydroboration oxidation. So, as I mentioned on the previous slide, hydroboration oxidation adds an H and an OH with anti-Markovnikov regioselectivity. So we use a two-step sequence. If we had Markovnikov addition, the OH would add here and the hydrogen would add here, but in the hydroboration oxidation process, we get anti-Markovnikov addition, where the OH adds to the less substituted carbon atom. Now, it turns out that hydroboration oxidation is also stereoselective, and the H and the OH are added in what's called a syn fashion. Right? And what that means is the H and the OH are added to the same side of the double bond. And so in the case of this alkene, we would get two products. We'd get the product where both hydrogens are added to the top of the double bond, or they're both added to the bottom. So in the one case, right, both the H and the OH come out on wedges. In the other case, they both come out on dashes. In hydroboration oxidation, we do not see anti-addition. In anti-addition, one group adds to one side and comes out on a wedge, and the other comes out on the other side and ends up as a dash. So in hydroboration oxidation, we only see syn addition. We do not see anti-addition. So one of the reagents that we use is called borane, and here we have a boron with 3 hydrogens in an sp2 arrangement, and we have an empty p orbital. And so this is very similar to the structure of a carbocation. And much like carbocations, borane is highly reactive because it does not have a complete octet. In fact, borane is so reactive, it often reacts with another BH3 molecule to form diborane. And in this diborane, we actually have what's called a 3-center 2-electron bond. And so we have 3 atoms that are essentially bonded by 2 electrons. So this is a relatively unusual bonding arrangement. Now, because we want borane and we don't want diborane, we often have to do something to help stabilize the borane. And so one way we can do that is choosing an appropriate solvent. And so if we use a solvent like THF, it will actually donate electron density to the empty p orbital on borane, stabilizing it. So we at least have some BH3 present in order to participate in the reaction. So the active reagent in the hydroboration oxidation is actually this BH3 THF complex. So on this slide, we're seeing the mechanism for hydroboration oxidation. And as you can see, it's a relatively involved mechanism. And so I don't think you need to be responsible for this mechanism, and so I'm not going to go through it in detail. I am going to focus on this first step of the mechanism to explain why hydroboration oxidation prefers anti-Markovnikov addition. So in the hydroboration process, when the borane adds to our alkene, the hydrogen and the boron add to the 2 carbons involved in the double bond in a concerted fashion. And there are a number of different arguments for why anti-Markovnikov addition is preferred. One such is that the hydrogen is less bulky than the boron with the H2, and so the hydrogen is more likely to add to the more substituted carbon, and the boron is more likely to add to the less substituted carbon. And so with the hydrogen adding to the more substituted carbon, this is what results in the anti-Markovnikov regioselectivity. So hydroboration is stereospecific in that only syn addition occurs. If my reaction results in only one chiral center, then I get a pair of enantiomers by adding the H and OH to either side of the alkene. And so I get a racemic mixture of the 2 enantiomers. Now, in the case of forming 2 chiral centers, again I get a pair of enantiomers, that result in, right, both the H and the OH ending up on dashes, or both the H and the OH ending up on wedges. But because we can only have syn addition, I don't get a mixture where we have the hydrogen on a dash and the OH on a wedge. And so in this case, we don't see the other mixed diastereomers where they would add by anti-addition. Okay, so let's look at an example of putting all this together. So we want to predict the products of the following reaction, and we can see that we're going to do a two-step hydroboration oxidation. And so because hydroboration oxidation is anti-Markovnikov, the OH is going to add to the less substituted carbon, and the hydrogen is going to add to the more substituted carbon. Now we have to be careful that we represent the correct stereochemistry of our product. And I haven't done that here, right? Both this carbon and this carbon are now going to be chiral, and so I need to represent that when I draw the products. And so we can have two different possible products. One where the OH and the H both add on wedges, and one where they attack from the bottom and they both end up on dashes. So my two products so I can have the OH adding on a wedge, and then if the H adds on a wedge, then the methyl group that I started with is going to be pushed down to a dash, and I'll have the other product where now the OH adds on a dash. Right? If the hydrogen also adds on a dash, then that means the methyl group that was there to begin with is going to add as a wedge. Now this problem is kind of interesting, so I think I've drawn the correct two products here, but in the previous examples we said that these two should be enantiomers. In this case they're actually not, because we had this existing carbon atom that was already chiral, and because its configuration isn't influenced by how the OH and the H are added, I do get two different products, but while these two have their configuration switching, because this one doesn't change, it turns out that these are actually diastereomers.